Oh, you already said this is the latest one?
Yeah, I checked.
All right, I'm gonna get people from the cafe and we'll. Forward and backward at the bottom, and then
Yep.
the top is the pointer behind.
Oh.
That's
It
just so
makes
that
sense.
people online. Started?
No?
Is it, no,
Button.
push the button. Interesting.
2 times.
Okay, now it should turn green. There you go.
Oh yeah. Oh yeah. Thank you.
All right, I think we have a break in incoming people, so we're going to get started. We have 2 more talks, I guess, for the T-Tory Star session for today. And our next speaker is Seok-Jun Chang, who will be talking about specially resolved Lyman alpha profiles in TW Hydra.
Thanks for having me. So I'm a postdoc at Max Planck Institute for Astrophysics in Gyeong, next to the ESO. So today I'm going to talk about the first detection and modeling of the specially lethal with Lyman alpha in TW Hydra. So in previous talk, especially Nico's talk, and emphasize why Lyman alpha is important. Also other talk today morning also emphasize that the UV radiation is crucial to understand the T-Tower star system. So, but in my talk, I just focusing on the Lyman alpha because this dominates the UV radiation of T-Tower star. The first of all is just a basic introduction about the Lyman alpha. Lyman alpha is one of the prominent coolant in the hot medium from the recombination or collisional excitation. So usually Lyman alpha line is strong, but the wavelength is too short to get from the ground observation. So I'm mainly working on a high Z universe, so that Lyman alpha line is easily detected ground observation. But the Lyman alpha is a strong line, but also Lyman alpha line can be scattered by neutral hydrogen. So if, for example, Lyman alpha emission from the emission region, but usually this hot region is surrounded, the cold region surrounded this emission region. So if Lyman alpha go into the cold medium, so Lyman alpha can be interact with the neutral hydrogen. We call it, this is a scattering. So from this scattering process, we just say this is resonant nature. Due to this resonant nature, the physical property of the H1 region are imprinted of the Lyman observable. So the scattering process causes three observable effects. One is spatially extended, also cause the complicated spectrum profile, and then polarization. So this is one simple schematic illustration of the Lyman the profile. So if the H1 medium is static, so Lyman spectrum becomes double peak. Because line center optical depth is really high, so Lyman photon has to escape at the line center. So static medium Lyman profile is double peak. But in the infalling gas, so Lyman scattered with infalling gas, the Lyman in lead world is suppressed by the infalling gas, and then the Lyman profile become blue asymmetric. So in the case of the alpha, this behavior is opposite. Lyman profile become red asymmetric. So this is one example of the Lyman observation. This is a Lyman blob in high universe. So size of this blob is over 100 kpc. It's the largest system. Also, the polarimetric observation Lyman is strongly polarized. The degree of polarization is larger than 10%. So it means this degree of polarization is hard to understand by the dust scattering or magnetic field because it's too strong. So also, and the KHWR observation result, this is the same old target, same object. This is the extract spectrum of each region of this Lyman blob. All spectrum have a different profile, red shifted, blue shifted, but don't exist the double peak. It's weird. But some objects also have a double peak. So it shows Lyman scattering exists in the cold gas. If the object have a cold gas. So T-Tauri star is the perfect object because it have a strong Lyman radiation or the cold gas scatter. So I'm not a T-Tauri star person because so that I cannot prepare like common figure because I made it myself. So Lyman emission mainly from the center star. So also Nichols, the paper showed a very nice the schematic illustration for Lyman alpha. If the strong jet exists here, this outflow in this jet make a red asymmetric Lyman alpha. So, or the Lyman alpha photon interact with the accretion flow. This is type of the inflow. Lyman alpha spectrum can be blue shifted. But I just wondering, so because also surface of the protoplanetary disk have a neutral region, so if Lyman alpha emitting from the central region, if Lyman alpha interact with the wind or disk, maybe scattered Lyman alpha is like specially extended, also we can get different Lyman alpha spectrum. So to get this Lyman alpha spectrum, we have to observe this target in the different position. The one is Lyman alpha from central star, and another observation have to do the location and off center region. So we choose and TW Hydri because this is the iconic face-on star. So this and lab 2 panel show the images of the protoplanetary disk by ALMA and IR images, IR observation. Also the helium-1 line show the P-Cygni profile, also Lyman alpha profile is the redshift. Maybe in the line of sight, this is based on object, but the line of sight, something outflow exists. So this is the background images is ALMA images. We observed the Lyman observed this target using HSD STIS slit. So using the five location. So this solid line is center slit, and other dashed and dotted line slit represent off-center slit. So observational result is here. I just normalized the spectrum by the peak of the Lyman alpha. So even through this slit have the offset like 0.4 arcsecond. This is roughly 40 AU, but Lyman alpha is detected. It's super nice. That means Lyman alpha suffers scattering and specially diffused by the atomic hydrogen in protoplanetary disk. So to analyze and this Lyman alpha spectrum, I first of all introduced previous study. Previous study, Greg get this Lyman-Alpha spectrum, but modeling is not quite good because like to understand this Lyman-Alpha profile, here assuming just the Gaussian emission and then Lyman-Alpha absorption, just the Lyman-Alpha absorption, like in this right side, this figure. So in the Lyman-Alpha source emitting broad Lyman-Alpha, and then this Lyman-Alpha observed by something outflow medium. But this modeling is good to understand the Lyman profile, but hard to explain spatial diffusion. So to decode the message of this special region with the Lyman-Alpha, I used my code. This name of the code, because it's a really new code, I not published yet, but name of this code is RT-SCAT, this radiative transfer simulation for scattering process. So this is grid-based 3D Monte Carlo radiative transfer code in this simulation. So each photon packet generated from emission region. So also assuming some scattering region, so each photon in simulation, I compute the scattering position by the physical property of a scattering region. So also, if photon scattered by the atomic hydrogen, I compute the scattering direction and polarization behavior by the atomic physics. So this is one of my paper is for Ullyses universe, but it showed a very nice special eligible Lyman-Alpha. The left panel is surface brightness of Lyman-Alpha. So in this paper, I assume point source of the Lyman-Alpha at the center. So the spherical halo surrounded this point source. So Lyman-Alpha scattered by this atomic hydrogen and make the special region of the surface brightness also strongly polarized. Also nowadays, I analyze the Lyman-Alpha spectrum from also Ullyses universe. Also this code can consider metal resonance line because the atomic structure of the metal resonance doublet is identical to the Lyman-Alpha. So that also this code can consider a metal resonance doublet. For example, the oxygen 6, carbon 4, and magnesium 2, nitrogen 5. So just back to the modeling for T-hydrogen, I consider two models. The one model is wind-only model because I believe so Lyman-Alpha formation of the Lyman-Alpha is mainly originated from the fast wind structure. So this model is for the formation of the Lyman profile. But as I say, Lyman-Alpha is specially diffused, specially extended. So also we can consider this component. So the second model is the wind disk model. So in this model, I'll explain the more detail in the next slide. But here, so I assume very, very simple disk model. So disk is composed of the two parts. Inner part is pure H1 disk, and outer part is just a pure dust disk. So in the pure H1 disk, so number density is really high, so 10 to the 7 per cubic centimeter. Lyman-Alpha photon cannot penetrate this disk. I think this is enough number density. So let's start from the wind-only model. So main parameter determine Lyman-Alpha profile is 3 parameter. So intrinsic width of the Lyman-Alpha and H1 column density of the wind and outflow velocity of the wind. So these 3 panels show the spectra considering different column density, input width, and the outflow velocity. So I just compare the Lyman-Alpha spectra in broad parameter range. I got found the best model. H1 column density 10 to the 20, outflow velocity 200 km per second, and then sort the Gaussian width of the intrinsic Lyman-Alpha is just 300. But this model, this parameter well reproduce Lyman-Alpha profile, but the problem is, so I also do the more observation using simulated result. So, and then I estimate the slit surface brightness. So in the right panel, so each point represent brightness of the Lyman-Alpha each slit. So I compare this slit surface brightness with the observational slit surface brightness. This is a result. So black and gray, the solid line represent observational slit surface brightness in the 2 direction because we have the 5 slit spectrum. So this blue dashed line represent and simulated the slit surface brightness for various wind size. So, but the ore surface brightness looks like it produced well, but in the 10 AU point is like simulated result always less than the observational result. So that I think the scattering on the disk can make a more special diffusion. So also wind-only model is good to reproduce the Lyman alpha profile, but to reproduce the special diffusion of the Lyman alpha, we need a disk scattering. So the next wind disk model, so I use the same parameter from the wind-only model in the wind of this wind disk model. This wind disk model is composed of the 3 component and bipolar wind, and then central Lyman alpha emission source, and the protoplanetary disk. As I say, protoplanetary disk is too simple. So after my talk, if you have some idea about the more detailed disk, please let me know. I can happy to adapt that. Anyway, here, so this component, this dust component is extremely dust optical thick. So the dust optical is 10 per 1 AU is Lyman alpha impossible to penetrate this disk. Also, H1 disk is really optically thick because the number density is 10 to the 7. Maybe optical depth of the Lyman alpha is larger than 10. Oh, larger than 10 to the 6, sorry. So using this model, also I get same slit surface brightness. So this green dashed line is slit surface brightness of the wind disk model. So it shows if the H1 wind size is larger than 50 AU, we can explain spatial diffusion of the spatial lesion of the Lyman alpha from HST observation. I have time. Out of time. Okay. Thank you. Okay, simply, I also compare the offset spectrum. If the H1 region is too large, like Lyman alpha just reflected by the disk, and then this reflected is not obscured by wind. In that case, some Lyman alpha photon is enhanced. So the one quick result is Lyman alpha, the wind is large enough to obscure the H1 disk. So I just quickly show the one result for general study of the Lyman alpha in T-Tauri star. I also compute the eternal Lyman alpha radiation. So the left is wind disk model, it's disk only model. So I compare with the eternal radiation field. I just quickly only test one figure because this figure represents the total luminosity of the Lyman alpha within the disk wind model and disk only model. So if the disk opening angle is large, also column density is high, so reflection effect is very important. Lyman alpha, the wind reflection helped Lyman alpha go into the disk. Yes, yes. Yeah, sorry.
Really quick question in the audience online. If you have any questions that come up, you just put it in the Slack and we can answer it.
Yeah.
All right. Okay. Our next speaker is Edwin Cruz-Aguirre, who will talk about also Lyman alpha profiles in T-Tauri stars. Thank you.
Hi, so I'm Edwin. I also go by Fernando. I want to first thank the organizers for giving me this opportunity to speak today. I'm going to be talking about these direct Lyman alpha reconstructions of T-Tauri stars. Before I get into the reconstructions themselves, I do want to take a step back and look at the big picture. It's not the picture you're thinking of, although it is a nice picture. And so as we've heard about in many of these talks that we've had throughout this workshop, UV light really does shape these protoplanetary disks. It will impact and dictate their chemical compositions, their structures, and their temporal evolution over time. And especially after that first million years or so of the disk, at that point the dust will start to settle enough for UV photons to really make their way through the disk and do all the things that we've seen them do throughout this workshop. And so I wanted to look at, take a closer look at the FUV portion of these T-Tauri spectra. So I have a collection of them here, wavelength on the x-axis and then logarithmic fluxes along the y-axis for a sample of these T-Tauri stars. And you'll notice in every single one of these, there's one common feature, and that's this really large emission profile, and that's, as you might have guessed, Lyman alpha. And Lyman alpha is the dominant feature in these FUV spectra. And here's a linear version of this plot to really appreciate just how much Lyman alpha towers over all of these other emission features. And I should clarify here, this is the Lyman alpha profile is seen close to that surface of the star. And in these profiles, or in these spectra rather, the Lyman alpha profile can account for something like 70 to 90% of the total FUV emission coming from these stars. And this kind of extends into the whole UV bandpass. It can be anywhere between 10 to 50 or so % of the total UV flux coming from these stars. So Lyman alpha being so strong, it's a very important driver for things like photochemistry within the disk and different fluorescence features that we see in different regions of the disk. And while it's incredibly important to know and understand what this Lyman alpha looks like, it's also incredibly difficult to observe it. And here I want to illustrate what the complications are with this figure here. So we have our T-Tauri star right over here. It's got its nice disk, and we're observing it with our favorite FUV instrument on the Hubble Space Telescope. The Lyman alpha profile close to the surface of the star might look something like what you see on the right there. It'll propagate through a accretion-driven outflow that has some atomic hydrogen in it, and that will attenuate some of that Lyman alpha light to give you a profile that looks kind of the gray curve over there. On its way to Earth, it'll pass through one or several clouds of the interstellar medium, composed again of atomic hydrogen, that'll further attenuate your Lyman alpha profile. And this isn't the whole story. HST is in orbit within the exosphere of the Earth. And within that exosphere is more atomic hydrogen, and that creates what is known as the geocoronal emission feature, or air glow, which is that purple profile on the right there. And what we're left with when we observe these Lyman alpha profiles is very different from how they first started, close to the surfaces of these stars. And so it's a really important line to know, but it's also really difficult to measure it. How do we go about this? And what's typically done is that we will reconstruct the Lyman alpha profile based on these fluorescence features that we see in the disk that are driven by the Lyman alpha emission. And so the idea here is that we'll have a Lyman alpha profile that passes through this outflow and looks something like what you see here by the time it reaches the surface of the disk. This Lyman alpha will then propagate its way through, excite molecular species such as molecular hydrogen and carbon monoxide. These molecules will then fluoresce in the UV, and we observe that in our FUV spectra. And the goal is then to try and figure out what the Lyman alpha profile looked like originally that produces the H2 and CO fluorescence that we see in the spectra. An alternate method is to perform direct Lyman alpha reconstructions based on what we see in our observed profiles, and there's an example of what that looks like here. The cost data is in blue, and then we can fit all of these different sources of emission and absorption to reconstruct and go back to what the Lyman alpha profile originally looked like before going through all of these things. And this is actually something I've done before, not quite for T-Tauri stars. A good portion of my dissertation work involved developing this tool in Python called Subtract Airglow that will simultaneously fit the airglow profiles on COST-U 130M spectra, as well as reconstruct stellar Lyman alpha profiles, but for main sequence FGKM dwarfs, not their T-Tauri equivalents. But while this tool cannot be used on the T-Tauri star Lyman alpha profiles, the model components themselves can be adapted to work in that different parameter space. And that's what we have done. So I wanted to look first at what these different Lyman alpha profiles look like. There's one that should probably be familiar to you now, these P-Cygni-like profiles. And the characteristic feature here is that the blue Lyman alpha wing is either completely or almost completely suppressed by this outflow. We also have these intermediate profiles where the red and blue Lyman alpha wings are more similar in amplitude. And then we have these inverse P-Cygni-like profiles that we saw before, where the blue wings start to be greater in amplitude than the red wings. And as Nicole showed earlier today, we believe that this kind of tracks along with the evolution of the disk as planets start to form and the dust and gas starts to dissipate. Oop, that went a little, that's fine. So we develop models to fit these Lyman alpha profiles. The general modeling pipeline looks something like this. We first start by co-adding the available G130M data for a given T-Tauri star. We'll then use that subtract airglow tool that I had showed before just to perform the airglow subtraction. It will attempt to try and fit all these other things, and it will fail to do so. But for our purposes, we just use it to get the airglow subtracted spectra, and then on that spectrum, we fit these new models onto the Lyman alpha profiles. And in the future, those last two steps will be merged into one. The goal is to provide an update to that tool to the community to do all of these things simultaneously. Okay, now it wants to do that, that's fine. So we did this for a number of stars, a sample of 17 T-Tauri stars that were available in the mass data archives observed with COST G130M, as well as have reported literature fluxes for these molecular reconstructions. And that's what's plotted on the left here. So we're looking at, on the x-axis, is the integrated flux of the intrinsic Lyman alpha profiles, or in other words, the profile as seen by close to the surface of the star. On the X is for these molecular fluorescence-based reconstructions, and on the Y are the results from our direct reconstruction models. Each of these points represents a different T-Tauri star, and then we have this diagonal line here representing the one-to-one line. And so we find that to within about a factor of 2, a good number of these targets show agreement between these two reconstruction methods, and to within a factor of 5, most of these targets show agreement. And this gives us some confidence that this method is actually capable of reproducing the intrinsic Lyman alpha profiles of these T-Tauri stars. So the next thing we wanted to figure out is how well does this model do at reconstructing and predicting what the disk is seeing from these Lyman alpha, what Lyman alpha profile the disks are seeing from their central T-Tauri star. And that's where things start to get a little tricky. So the way we went about this was we took our outflow attenuated profile here in gray, and we used that as an input to a molecular hydrogen fluorescence model. And our initial results look something like this. We have the COST data shown in blue, and we have our synthetic H2 spectra shown in red. And we find not a terrible match. There's a few places you'll see here where our synthetic spectra kind of over-predicts the amount of H2 emission than what we actually see in the data, and that is to be expected to an extent. We know that below about 1450 angstroms or so, that there is going to be some amount of self-reversal observed in these H2 emission features. But this is kind of the best we've been able to do in terms of trying to predict the H2 flux. It's usually not this good, and that is because we found for a number of our targets, our reconstruction models, our two absorbers, the ISM absorber and the outflow absorber, tend to compete with each other instead of cooperating in terms of trying to fit the total absorption. And we'll find more often than not that the outflow profile wants to compensate for all of the absorption seen in the Lyman alpha profile. And it just leaves a very little amount of Lyman alpha that's supposedly reaching the disk. It really doesn't give much to be pumped into those H2 fluorescence lines, and we get a very poor fit to the data. And so this is kind of where the Ulysses data comes in now. We've identified about 50 or so targets within the Ulysses library that are good matches for performing these Lyman alpha reconstructions. We think that we would be able to apply our models to them. And this would about quadruple the number of targets that we've been able to do this kind of reconstructions for. And the goal of this would be to, using this expanded set of T-Tauri stars and their different profile morphologies and different points along their evolutionary tracks, that we can further calibrate these models to be more applicable to a wide set of T-Tauri stars, as well as do better, make better predictions of what is actually reaching the surfaces of these disks. We can also explore some interesting edge cases. For example, if we have just a faint T-Tauri star, maybe it doesn't have It has some H2 in their spectra, but not strong enough to perform molecular reconstructions. This method could be a powerful alternative for trying to reconstruct it if the Lyman alpha is bright enough, or maybe start looking at things like transition disks. I think that would be an interesting case to try and apply these models to and see what we get out of that. So just wanted to quickly summarize here some of the points of this talk. The ultraviolet, and particularly Lyman alpha emission, is from these T-Tauri stars is really important for determining the structure and evolution of their protoplanetary disks. The Lyman alpha emission will drive photochemistry as well as fluorescence within these disks, but is challenging to observe directly. And by adapting these main sequence stellar reconstruction techniques onto the T-Tauri star parameter space, we can reconstruct well enough the Lyman alpha profiles of these T-Tauri stars close to the surfaces of the star. Additional modeling work is needed to further predict what the disks are actually seeing from the Lyman alpha profiles. We would like to use the Ulysses data to refine these models, and the ultimate goal here would be to provide these Lyman alpha profiles to the community, as well as this updated tool that anyone would be able to use to perform these kinds of reconstructions however they would like. Thank you for your attention.
Questions? Thank you, Edwin. Yep.
That was a really great talk. I have a couple of questions.
Sure.
One is, do we have like separate observations of the air glow that you can use that you're using to inform your subtractions, or is it kind of just a best fit?
Yes. So part of the development of this subtract air glow tool, once I get to it, the first part of this project was to develop these air glow templates. So what we did was there were archival observations of air glow captured by different grading observation modes of COS. So we use those to create these templates, not just for Lyman alpha, but also for the oxygen triplet at around 1300 angstroms as well. So those are already preloaded into this tool.
Cool. And the other thing is one of the two reconstruction methods more reliable than the other?
At this time, I would say no. They're kind of complementary to each other. We found that within about that factor of 5, they seem to be reproducing similar results.
Anything online, Elaine?
Thanks. So I had a question about when you reconstruct the Lyman alpha profile, and then you're examining its impact on the disk. Mm-hmm. So is the actual profile the most important thing, or is the absolute flux the most important thing? Or put another way, is it enough to get the flux of Lyman alpha approximately right, even if the profile isn't exact, and you'll still get the same effect? Or do you need to really reconstruct the width very accurately to, say, predict the H2?
Sure. So I think getting the profile shape is pretty important. The H2 features are going to absorb at very specific parts of this profile. So knowing, I guess, within those wave bins, it's good to know what the absolute flux in them is, but you do want a general idea of what the shape of this profile looks like.
We have to move on. Ed, you want to come get set up? Let's thank Edwin again. And we're going to switch gears now and start our session on the ISM and the CGM. I'm very excited about that. It should be, you already loaded the correct version this morning, right?
I just put it in my pocket.
Did you
It'll still work.
push the button?
What?
Did you push the button on this
Ooh.
green light?
It's green light. Okay.
Our first speaker of this ISM session is Ed Jenkins, who is going to talk about depletions in the Milky Way and Magellanic Clouds.
Okay, if you look at the spectrum of a hot star, you see not only stellar features, but interstellar features. And you can then judge the strength or the amount of different elements by looking at the strength of the lines. You normally expect the total abundances of the interstellar medium to be equal to that of early type stars. But what you find is that the atomic abundances are depleted by the formation of dust. So doing this study with the Magellanic Clouds gives us a chance to understand the behavior of the depletions as a function of metallicity. We have the LMC, which has mild lower total abundances, and the SMC is much lower. Now, why is this important? Well, first, we want to find out if the depletion pattern across different elements change when you go to the lower metallicities. In addition, when you want to find out atomic abundances in very distant systems, those belonging to damp Lyman alpha systems with a Z greater than about 2, you can only look at the absorption lines. You have to understand how the dust modifies the strength of those absorption lines if you want to get any sort of handle on the elemental abundances of these very low metallicity distant systems. Well, I did a study back in 2009 characterizing the pattern of dust depletions in our own galaxy. Later, there were some smaller studies of the LMC and the SMC, and now with the Ulysses data, we can expand that sample by a significant amount. We've basically doubled the LMC targets and tripled the number of targets in the SMC. We use the E140M shell data because that provides enough resolution that you can get reliable column densities. Okay, how does this work? Well, you take the observed abundance, the log of the observed abundance, let's see if I can use it, and you subtract from that the stellar abundance. And from that you get a logarithmic depletion factor, which we call delta sub x. That's always a negative quantity. You can then infer the amount of material in the dust by this simple formula at the bottom. Basically, the dust to gas ratio is equal to the metal to gas, as indicated by the stellar abundances, and then the dust to metals down here. You have to have some idea what the abundances are in the stars, and they're generally consistent with the solar abundances, except when you get down to carbon and nitrogen. They seem to be more underabundant than the rest of the elements. Now that's an interesting clue as to something interesting may be happening when you look at the interstellar medium. And indeed, in other systems, there seem to be deficiencies in the carbon to oxygen ratio as you get down to very low metallicities. In the Magellanic Clouds themselves, if you look at a quantity called QPAH, which is the ratio of very small aromatic hydrocarbons through the amount of silicon dust, you find that in the LMC, the amount of this parameter is about the same as in the Milky Way. But in the SMC, there is an underabundance of the PAHs, perhaps caused by the underabundance of carbon. Well, what can we measure? Here is a list of elements that have transitions in the UV that we can record. Unfortunately, for C, N, and O, we can't measure them because either the allowed transitions are badly saturated or the forbidden lines are just far too weak. That's unfortunate because most of the material in dust is in carbon and oxygen. We can measure all of the other elements except for sulfur because, well, actually you can measure it, but there's a very strong contamination by material in the star's H2 region, and I'll discuss that later. Okay, elements seem to deplete in lockstep with each other. I show at the bottom here on the x-axis is what I call a depletion factor. That is, that's the severity of the depletion along any particular line of sight. The observed depletion on the y-axis, again that's logarithmic, you can see that for all the lines of sight, they all follow this F-star trend, but at different rates, depending upon whether you have a volatile element or a refractory element. Titanium depletes very rapidly, whereas germanium and surprisingly even krypton, a noble gas, depletes less severely. Okay, this is consistent with a picture of where the abundances of the atoms decrease in an exponential fashion with time, which is what you'd sort of expect, but with rates that differ from one element to the next. And you can think of that depletion as kind of, the F-star is kind of the arrow of time as the dust grains grow in the interstellar medium. And that arrow reverses when the dust is destroyed by shocks from supernovae. I talked about the F-star parameter. There's another parameter that's been adopted by other people, which is to measure the ratio of zinc to iron. Zinc depletes very slowly, iron depletes more rapidly. Well, here's an interesting overview of what happens in these three systems. This is from a paper that Julia published some time ago. And you can see there is a trend with the hydrogen column density. That is, the relative abundance of silicon to hydrogen decreases as you get an increasing column density of hydrogen. But also you find that this trend is the same in the three different systems. Since this quantity here for a given hydrogen column density is the same for the three systems, and yet this goes down, it means that the dust to hydrogen ratio decreases more rapidly than the metallicity goes down. And that makes sense, that once you have a lower metallicity, the atoms can't find each other as easily, and so they don't condense as rapidly. The DLAs, it's just kind of a mess. Okay, you can then measure the mass-weighted dust-to-gas ratio, and here we have it for the three different systems. Here's a repetition of that same plot, this time for iron to hydrogen in the Ulysses results. And I've color-coded it for the different systems. And you can see they all fall up on top of each other. And you can see this trend with hydrogen column density for the three different systems in these three plots. In the case of our galaxy, I'm really giving you the average volume density of hydrogen. It's just the column density divided by distance. Whereas here, we're using only the column density, which is equivalent to a space density if you consider that the gas in the system has a given scale height everywhere. And so at the higher densities, you get more complete depletion, which again makes sense. That's what you would expect. This is confirmed by studies of infrared emission from dust. That is, the dust to hydrogen ratio increases as you increase the surface density of hydrogen. Now, there's a problem, and we have to deal with it. If you look at the depletion of sulfur, you get positive depletions at very low values of F star. And that just doesn't make sense. You're now getting sulfur column density relative to hydrogen that's larger than the stellar counterparts. Why is this? Well, the problem is that you can have some singly ionized sulfur inside the star's H2 region, which contributes to the column density. But since the hydrogen is ionized, the hydrogen is not counted in the total. And you can see this in the plot on the left. This is from a cloudy calculation of what the sulfur 2 space density is as a function of radius out in the Stromgren sphere. Sometimes you get a large accumulation, as seen on this edge here, because you're density bounded, whereas here the photons can escape and you don't see so much. Well, here's a picture of the LMC. It's a very complicated situation. How do we figure out how much hydrogen to subtract to give us the right abundance ratio? It's very hard to think you can do it on an individual system. So what we try to do is to do it collectively on the premise that things will average out and you'll at least see a trend that looks about right. If you look at the spectrum of a star, here's a plot of the photon flux as a function of energy for stars of a different temperatures. And then I plot above it the photoionization cross-section divided by the total recombination coefficients. That's both radiative and dielectronic recombination. That ratio gives you a measure of how easy it is to ionize the atom above the singly ionized state to a doubly ionized state. It's the singly ionized that we're looking at. Well, the helium-1 ionization potential is around 24 electron volts. You can see that most of the cross-section for sulfur is above the helium limit. Helium opacity cuts the stellar output for the cooler stars, and it also attenuates the flux inside the Stromgren sphere. You actually have a helium Stromgren sphere inside the hydrogen one. So these helium ionizing photons are severely attenuated, and that leads to the fact that the sulfur is not easily depleted, or not easily ionized to the higher stage. So we have to deal with that contamination. What about other elements? Well, if you look at these refractory elements, you can see that they have at least some response below the helium limit and a very high cross-section above the limit. These particular elements are not subject much to contamination from the H2 region. The elements magnesium, phosphorus, and silicon are sort of in between those two. So we got to watch out for those elements possibly having this contamination problem. And zinc is kind of weird. It has some cross-section below the helium limit, but it's a very, very low value, but a very high value up beyond the limit. So that's going to be very dependent upon the stellar temperature. We can get some guidance by looking at actual results, and what I've shown in this table is the results for a component that's fully ionized in front of gamma-2 velorum. And you can see that if I normalize it to the sulfur over here, you can see there is some response of magnesium, silicon, and phosphorus. These are logarithmic factors. But manganese and iron are pretty much immune to this effect, as you would expect. Well, how do we make this correction? What you want to do is you want to know how much hydrogen you've got to add to the measured hydrogen to then make a comparison of hydrogen to your element a fair one. Well, one way to do it is to look at where you get zero depletions. That generally happen if you look at the refractory element, you get a crossover at zero depletion at F star equal minus 0.75. And correction, if you add it in there, you can then alter the response to agree with that. Now that is dependent upon whether or not in reality this extrapolation works for every element. We know it does for some, but there's no guarantee that that is the case. Nevertheless, you can get some reassurance from results of looking at damp Lyman alpha systems. Here is that you've got a sight line to a quasar that's penetrating some foreground galaxy. It's not very likely that you're going to be going through an H2 region. With the stars we're looking at in the Magellanic Clouds, you're always ending up in a star's H2 region. So if you look at the results, these are plots now using zinc to iron, but that's sort of equivalent to the F star parameter, the severity of depletion. You can see that they all more or less extrapolate at the same point. Zinc to iron equals 0. So that gives us some reassurance that this adjustment is a valid process. It shows the effect of adding extra H1. The uncorrected results for magnesium in the SMC can be corrected to give something that's more reasonable. The effect is not large for the higher depletions, but the lower depletions is very important. So the other way to do this, the other effect, is to actually calculate from the atomic parameters how much hydrogen there has to be. And this amount of hydrogen depends upon the element, because it depends upon the element's atomic parameters and how the responsiveness is in the H2 region. Well, for any particular element X, we have a measurement of the H1. We want to know how much H we should add. It's given by this very simple formula here. The ratio of the recombination coefficient of element X to that of hydrogen, and comparing that to the ionization rates. And that ratio holds for almost any electron density. It is also valid if you have multiple stars in the H2 region, and the dependence upon the star's temperature is very weak, because these two quantities, the ratio of those two quantities doesn't vary much as you change the stellar temperature. So this is a nice way to do a global correction, but it only works if this quantity is much less than 1. That is, the singly ionized is much less than doubly ionized. You can do it when this inequality doesn't hold, but it's more complicated. All right, here are the results. I'm now showing you the depletions at F star equals 0.5. Now, this is a moderate depletion for our galaxy, but what is sort of the highest depletions you'll find in the Magellanic Clouds because of that effect of the lower metallicity not making such strong depletions. You compare them with each other, they're pretty similar, but there are differences. You can see, for instance, that phosphorus has much less strength of depletion than in the Magellanic Clouds. Titanium has stronger depletion than in the Magellanic Clouds. And I should point out, I mean, these are decks. So you go 0.3 decks, that's a factor of 2 difference in the strength of the depletion. There's also rather large differences in manganese, and likewise for zinc. Now, why is that? You would expect in those systems, if you have a lower metallicity, that's just equivalent to adding more hydrogen. And yet, the trend from one element to the next changes. My conjecture here is that it may have something to do with that reduced carbon abundance. That is, less of the PAHs around, which serve as the nuclei for condensation, may alter then the rate at which different elements deplete. Okay, let's look at the dust composition. Now, if I do that at F star equals 0.5, I would just get the stellar abundances. So if we go to F star equals 0, which is fairly light depletion, you can see the tops of these bars are equal to the stellar abundances. Then the dust abundance is given by the tops right here, and what's left over for gas is this area in between. Again, 0.3 dex is a factor of 2. So you can see there are variations in the dust composition as you go from one system to the next. Let me now end with just a particular observation that's interesting. You expect dust to be destroyed when there are shock waves, either from supernovae or from the mass loss from stars. If you look at the residuals between the expected depletion based on the hydrogen column density in that trend, the deviations are shown here on the x-axis. As here are the residuals. You have excess in this region and a deficiency here. That seems to, at least in the LMC, seems to correlate with the spread in velocity that you can see at the extremes of the 21 centimeter profile in that direction. So gas that is more stirred up has a weaker depletion. Again, that's what you would expect intuitively. SMC, it's not so clear. Now, what about let's look at whether or not the stars are within H1 shells. They've been identified, and the question would be, do you see any trend there? And to my eye, there's not a clear trend. So whether or not you are in projection going through what people think are H1 shells generated by the stars, there doesn't seem to be a very clear-cut dependence. So now I'll end my talk with the principal conclusions, and I'll take your questions. Thank you.
A few questions. Thank you, Ed. You see anything online?
Just about the first point here, I'm pretty sure there's a very simple explanation, but I don't know it. Why is it that CNO can only be measured for the Milky Way?
Oh, because you can see the forbidden lines. That is, in the Milky Way, you have targets that are bright enough that for reasonable integration times, you can see for oxygen, you can see the 1355 line. For carbon, there's a forbidden line of 23 something or other. But you have to have extremely high signal to noise because it's such a weak line that was only able to do that with GHRS. And the reason is that you have to have very high count rates to get the signal to noise. And GHRS could tolerate very high count rates in bright stars, whereas this cannot. So we're looking at a nitrogen fine structure line.
So I had a question about, does this depend, what's the dependence of these behavior of different element depletions on the original dust properties that are sort of injected into the ISM, or is that all wiped out at some point?
Well, I think it does make a difference because in the atmospheres of stars, you are ejecting the smallest dust particles upon which they grow, the grains grow as you're in the general interstellar medium. And if you change that composition in the stellar atmosphere, you're then changing the nature of the seeds upon which the other elements deplete onto. So I think at least that's my interpretation. It's a conjecture on my part, but it seems like a reasonable approach. Otherwise, I couldn't explain it. If the carbon and oxygen abundance, if the carbon was normal, then I would say, well, then why are they different? Because again, it's just like adding more hydrogen.
Thanks, Ed. Thank you, Ed. We're going to move on. Jan, come over.
Of course.
Yes. Can people hear me? Okay.
All
So hello everyone, I'm Yong. I am very well aware that I am the one sitting between you and lunch. So I'm gonna make this semi-entertaining, and I'm also gonna ask you to participate in this talk a little bit. So I am one of the handful of people that studies the gas using the Ulysses data set. I think this is one of the most interesting workshops I've ever been to. We talk about planets, stars, outflows, ISM, and then galaxies. Where's the, I see. So I just want to put everyone on the same page. So this is a cartoon illustration of our own Milky Way galaxy. But what I'm going to say is pretty much true for any type of galaxy, smaller or bigger. So in this galaxy, we are here. We are off-center at 8 kiloparsec away. And then we are surrounded by stars in ISM, which is the topic in this workshop. At the same time, if you look at, you see all these very pretty status streams, and the status streams are pulled out of dwarfs such as NMC and SMC because of the tidal interaction between this galaxy and their host galaxies. And all right, so now let's think about the stars and the ISM. And this is something I borrowed from my colleague, Jeff's work. I'm going to ask everyone to take a deep breath on 4 counts. Okay, ready? Breathe in. 1, 2, 3, 4. Hold it. 2, 3, 4. Let it out. 2, 3, 4, 5, 6, 7, 8. Okay, great. Hopefully you have a clear head for the remaining of the content now. But at the same time, congratulations, because you just participated in the cosmic baryon cycle. And why do I say that? That's because the things that you breathe in and out, what are those? They are hydrogens, carbon, and or whatever things that's in your body, like oxygen, iron, silicon, anything. They come from the ISM in the stars, right? So especially for massive stars, they are formed, and at some point they blow out, so they are going to send a lot of stuff into the space. And this is a space that's what we call the circumgalactic medium and intergalactic medium. And all the baryons and battles are going to hang out this space for a long time, billion years, and at some point, some of them decide to come back into the galaxy to participate in the next cycle of star formation process. So this is really the process we call cosmic baryon cycle or cosmic ecosystems. They are kind of the same thing in my mind. So in these systems, the reason why I bring this up is because the things that helped the baryons and the metal to travel between different points are inflows and outflows. So that's why it is important to study all different gas dynamics in this system for us to understand how you detect all these things. So this is a cartoon illustration. I'm going to show you what we measure. So this is a plot that shows you on the x-axis the stellar mass of a galaxy, so Milky Way on the right, SMC, NMC, all smaller galaxies on the left. On the y-axis, so this is the total amount of mass you expect in a particular component. And then 1 being what's predicted by a lambda-CDM cosmology, basically. And then in red, these are the total amount of mass you expect to find in a star. And then in blue is the total amount of mass you will be able to find in ISM. Some looks really weird, right? Because they're only about 10 to 20% of the total mass that you can find in a star in the ISM, compared to what's predicted from the lambda-CDM cosmology. So this is saying the rest of the blank space here, this is the space where we expect to find stuff in the CGM. So that's why CGM is so important for any galaxy people, because it contains a huge amount of mass that's critical for evolution and formation of a galaxy. And then, of course, if you look at this really tail end where NMC and SMC lies, the fraction of the baryon that's missing is even worse. So that's a story about baryons. Now, metals. So I'm going to show you the amount of metal that we can find in the ISM and in the star. And I'm going to show you a chart about the stellar mass, gas phase metallicity, but the same thing is true for the stellar metallicity. Again, this is the stellar mass, Milky Way on the right, and the NMC and SMC on the left. On the y-axis, some people might be familiar, so this is the gas phase abundance. The value doesn't really matter. The thing that matters is if you find a higher value, that means you find a lot more metals in the ISM. If you find lower value, that means you don't find that much metals in the ISM. Through tens of thousands of data points. So there are a lot of observational data points here, which is the curve, and also measurements of the nearby galaxy and also simulations. You see this very coherent trend of what the stellar mass gas phase metallicity look like. On the high mass end, you see that the metals in the ISM doesn't really change much for Milky Way mass galaxy on that end. This is what we start to begin really curious, because on the really low mass end, you see that as the mass goes lower and lower, if you look at the teeny tiny dwarf galaxy, you don't find that much metals in the ISM anymore, and you don't find that much metals in the stars. So lower mass galaxy generally retain much less metals in the ISM compared to their higher mass counterparts. The reason for this, why there's a huge space here, this is because outflows may have carried all those metals into the space beyond the ISM in the star, which is the CGM. So that's kind of the first part of my talk, which is to give you a reason to believe me why outflows is so important, why we need to spend so much time to understand outflow. This is because it is a very critical recipe to make a very realistic galaxy in simulation, and also it's important for evolution of the galaxy. All right, now let's come back to the NMC. So this is a cartoon illustration of the NMC star-forming disk. So the disk itself could be much bigger, but I'm only showing you the star-forming disk in the center, the SMC, and also the Milky Way. So the relative position are more or less true to the present-day locations. Ulysses probed the front side of all the gas structure in the NMC, outflow, and anything in the foreground, basically. Now, here I'm showing you the distribution of Ulysses sidelines. And I'm only showing you DR5 because that's where my analysis was. And in DR5, there are 110, but in DR7, we have 182. So in Kat's talk yesterday, you see that there are like beautiful data coming out of 30 Doradas and also other H2 regions. So that is where most of the Ulysses sideline clustering at. At the same time, I would like to point out, if you look between the H2 regions, you see some sidelines here and there. I am deeply grateful that Ulysses team had thought of looking at regions that are not very close to H2 regions. So Ulysses is such an amazing data set that can help you understand a lot of things across very different star-forming regions in just one galaxy. Amazing data set. Let me just show you one spectrum. So this is, I have taken out the stator features. So you're looking at only the ISM absorption here. And you see three components color-coded in three different ways. First of all, this is the Milky Way, interstellar median absorption, and also the IVC. Ananya is going to talk about this right after lunch, and she's come back. That talk is going to be great. And then there's going to be another feature that Kat talked about yesterday, is the IVC here. Finally, the NMC is this blue, huge extended emission from one side to the other side. So that's the outflow I'm going to be focusing on. And keep in mind, this is just one sideline. And you see this kind of features basically across the disk, everywhere. Now, I'm going to do a polling task, which is to talk about static spectrum in front of static experts. And so this topic has not been brought up, but I actually think it's a really important topic, because as much as I love Ulysses spectra, not every single spectra can be used to study in the CGM and the ISM. Let's take a look at this one. So, so this is a chunk of the silicon-4 doublet. So this is silicon-4 3093 and 1402. In gray, I have highlighted where the Milky Way NMC absorption should be. So it spans across 500 kilometers per second. Anyone want to take a guess? What's the spectral type of this star? Julia? Yes. It's one of the very rare type luminous blue variable in the NMC, and this is one of my horrifying nightmare, basically. Anyway, so I don't need to convince you that nobody should use this star to study the ISM in the CGM, because it just looks so bad. The reason why it looks bad is because the stator feature you see here has a very similar width compared to the ISM feature. So there's no reliable way to back out the signal. So for the past 2 years, I've staring at spectrums like this for a long time. I come up with two rules. The first rule, which is the less wiggles, the better. The wiggles here refer to any static features you can see. So here's an example of a sulfur 2, 1250 and 1253. And then in red is the static model continuum fits that we put on. In this case, you see that the static feature kind of just very minimum, and you can take out the ISM feature very reliably. So that's rule number 1. Rule number 2, of course, in a lot of the regions, we don't expect very smooth static features. In that case, we want it to be the wider the wiggles, the better. By that, I really mean p-Cygni profiles. This is one of the amazing cases. I love p-Cygni profiles. So again, this is silicon-4 is a late O-type star. And in red, I am showing you our model p-Cygni profile fits to the data. And then in gray, this is where the ISM absorption is. It is very clear that the ISM absorption is so narrow compared to the static features. You can separate these two very cleanly. Then, of course, I'm showing you one of the best case. I can do something that's a little difficult. So for example, this is a static wing that has low opacity and with non-opacity features. Totally cool. The ISM feature is here. We can take it out. And then this is a Wolf-Rayet star, has a relatively low terminal velocity wing. That's OK, too. Some of the Wolf-Rayet stars are just very difficult, and they have their own personalities. But it's OK. I don't know where the wing feature is, but the ISM feature is very narrow. We can also look at hotter wings, such as carbon-4, in which case you also see a very pretty p-Cygni profiles, right? So the reason why I show this is because my main purpose is to study the ISM and CGM, but I have all these very interesting byproducts of noise-free, ISM CGM-free static wing features that might be useful to some of you. So that's why I want to present here. So we're going to publish this data set. We are calling it NMC outflows because I can't think of any smarter acronym for this, and I can't call it Ulysses, of course. And we're sending the data to Space Telescope at the moment, but I just want to show you what it looks like. Every star has an interactive interface where you can zoom in, so it's very much similar to what Joe showed yesterday. So this is sulfur 2, our model fit to it. Now zoom out. This is silicon-4, the p-Cygni profile fit, and the ISM feature. Now back out. And then carbon-4. So my goals here is basically, this is kind of a very difficult task I have worked on for the past 2 years, and I would like to share this, and I would love to see what can come out of all this static wing feature fits, basically. Right, so if you're interested, please come talk to me. All right, back to the NMC. So for the rest of the 10 minutes-ish, I want to focus on what we learned from this blue absorption here. First of all, you see this picture before, so this is H-alpha emission, right? Now I'm going to show you what the carbon-4 look like. So now this is basically the NMC plane deprojected. So 1 degree is about 1 kiloparsec. And blue pixel here shows outflow, and the bluer the pixel, the faster the outflow. So like Kat said yesterday, near 30 Dorados, you see faster wings coming out, and this is in carbon-4. It's also true in silicon-4 and sulfur-2. At the same time, you see this slower wing, about 30 kilometers per second, that is in regions that is not close to the major H2 regions. So that's one major findings we find in this work. And second work, so for the outflow column density, so this tells you what is the total amount of material you can get along the line of sight. And then this is as a function of star formation rate, surface density. So what this is telling you is the higher the star formation rate, the more outflow stuff you're going to get. So there is a very nice correlation here. You can also see it spatially. So near 30 Dorados region, the column density is just so much higher compared to the rest of the regions. So this is also the saturation that I talk about. Most of the sight lines here are super heavily saturated because we're dealing with so much stuff along the line of sight. All right, so coming back to this broader picture, I would like to discuss two very broad themes with you. One is, as Kat said yesterday, the NMC is moving in the halo of the Milky Way. So it's actually enveloped in a bigger environment. So I'd like to discuss how does the Milky Way's environment impact the gaseous structure of the NMC. And so first of all, let's take a look at the kinematics of the galaxy. I don't know if you're familiar with plots like this. I like to call it spider diagram because this kind of shows you a rotating disk. So one side of the NMC is moving faster away from us, so that's in pink. The other side is slightly moving slower but still faster away from us. So you see like a nice rotation pattern in the neutral gas. And this is kind of just normal for on a DC galaxy. Now this is carbon-4. I believe this is actually the first map of the ionized gas for a galaxy, and thanks to the Ulysses data set. So in carbon-4, you see that the carbon-4 outflows show a similar rotation pattern with the north side moving faster away compared to the southern side. And what this is saying is the outflowing gas is moving at a very similar rotation pattern compared to the neutral gas in the NMC. So the ionized gas here is actually feel the gravitational pull of the disk very strongly, and it's not impacted by anything outside of the NMC. So perhaps the outflow is shielded by something. So my collaborator and I put out a scenario, which is a bow shock. So there has been other work that's been done that discussed there, like corona work. I encourage you to check it out. But here I'm going to put out a different scenario, which is, let's think about the dynamics of the whole galaxy system. The NMC is moving in the Milky Way halo at a velocity about 320 km per second. And the sound speed of Milky Way CGM is about 160 km per second. So that means the Mach number we are talking about is 2. And the Mach number could be higher if we are talking about cooler gas, which is totally reasonable. That's saying we should expect a bow shock like this. So my collaborator and I ran a simulation in which we model how the NMC move in the Milky Way, and we find that there is this bow shock structure that envelopes the disk of the NMC, which is in the center here. Of course, we have to prove it as an observer. So I think this is something that's quite challenging to approve, but we have some tentative evidence. First of all, if you look at the SMC and NMC H1 distribution, you see this compressed edge, and that's believed to be formed by the run pressure from the Milky Way's CGM. So that's one tentative evidence. The second is the H-alpha emission, where you see the morphology of the H-alpha emission actually match up with the morphology of the bow shock pretty well overall. So that's the first thing I want to discuss. The second thing is, I believe it's you who asked the question is, what does the NMC alpha look like compared to other galaxies? And so let me show you some evidence. So this is on the y-axis, the velocity of the outflows compared to the star formation rate surface density. So the scaling relation like this is very typical in outflow literature, where you investigate how that's outflow driven by star formation activity. NMC is in red here. So it is moving at quite a low velocity between 20 to 60 km per second. That is the center of the mass. And then compared to the rest, so these are star-bursting galaxies that drive much faster and more violent outflows. The main takeaway for this is there is this coherent picture, or there's a universal relation between the outflow velocity and the star formation rate surface density across 4 orders of magnitude that we are talking about here. All right, so let me put this in an even bigger picture. So now I'm going to give you a very quick review as to what the outflow literature look like. So this is not exhaustive, but I wanted to highlight why Ulysses is so important on this parameter space. On the x-axis, I'm showing you different tracers that have been used to study outflows. So this is the electron volt, and then we have something like sodium 1, oxygen 1, H-alpha, H-beta, then we go into lower ionization state, like iron 2, silicon 2, then higher ionization state, like what I do, carbon-4, X-rays. This is a proxy for the temperature. So this is relatively cold outflow, warm-ish, and very hot outflows. This is what the landscape looked like. So in observations, pretty much across very low mass galaxy to very high mass galaxy, there have been a lot of study across the cold outflow, warm outflow, or hot outflow, and there has been some study by Kat and by previous people on the NMC as well. And then, of course, there are a whole bunch of theoretical people interested in outflow. That's totally cool. And Ulysses is here. So Ulysses studied the NMC outflow that's around 10 to the 9, 10 to the 10. and you probe a relatively hotter outflow around silicon-4 and carbon-4. On this plane, the NMC may look quite underwhelming because it's just one data point, but don't blink. So now I reorganize it in terms of the methods that have been used to study outflows. On the bottom, this is what I call unresolved. So this is basically you have one sightline per galaxy. On the galaxy so far away, you have to stack a lot of things together. And a lot of amazing studies have come out of this, basically. On the top, this is resolved outflow. Either you have integral field units, so you resolve emission spatially, or Ulysses. You have over 100, close to 200 sightlines sitting here that just tell you what the resolved outflow look like in that space. And this is why I feel deeply grateful for all the Ulysses people here, because I'm willing to bet in the next 20 years until the HWO comes online, there's not going to be a data set that's going to beat that one. So this is like an amazing data set to study outflow over a very small scale. And then as a shameless self-promotion, Grace and I have our new HSC program coming online. Then we have 8 sightlines to study outflow in a lower mass dwarf galaxy in Sectans A. So stay tuned on that. All right, so that's kind of my summary slides. It comes a little fast because I want to send all of you to lunch quickly. But if you don't get anything out of this, totally cool. This is my summary figures where you can download from my papers there that kind of just summarize all the things I want to say in this talk. Thank you.
Thank you, Young. Questions? Yes.
In carbon, you listed carbon-3 and carbon-4. What does it tell us about the temperature distribution of the CGM?
So
both of them.
They are actually in very, very different wavelengths, actually. So I think there has been some study as to what the ionization structure and the temperature structure look like. But I would say the conclusion is quite nebulous at this point. We know that it's on the range around 10 to the 4 to 10 to the 4.5-ish, but there hasn't been a lot of very detailed study as to this. But I think Ulysses will be really useful because there are a lot of sightlines very close to each other, in which case that when the sightlines are really close to each other, you can tell what's the difference between the sightline. So there might be a lot more temperature and ionization study coming out of Ulysses sightline, basically. But I would say so far, we don't know like the nitty-gritty detail of the temperature structure. We know a range.
Joe Vasquez, TCU. So I have also have experience with how fun fitting those that continuum is. So what did you use to model your stellar spectra?
Yes, great question. That's something I thought for a long time. So the traditional method to model profiles like this is you take a relatively smaller chunk, for example, somewhere here. It looks relatively flat so that you can fit a low-order polynomials. So this is actually totally fine for a lot of stellar features and also for quasars. And it has been used in the field for a long time. But I think Ulysses kind of just pushed us to the edge because there are so many stars with really weird structures in it. So what I have been using is something called Gaussian process. And it's this non-parametric process that assumes that every model has a possibility. And you have to study the possibility by masking out the installer feature and then use the rest of the model to study what the shape look like. So I detail this in my paper as to how I work.
Okay, I'm going to repeat that. Can you make it? This is a question for who asked it? Oh, Sally. Yeah. So for saturated carbon-4 lines, can one get the column density from line ratios?
Short answer is no. So I did not explain in details here. Most of the carbon-4 is saturated, so that is where the open squares are. And this underline, you kind of just see the absorption hitting the rock bottom. You have 0 flux in it, right? So that's why I show the lower limit detections. So for these cases, there have been some correction methods in the fields to correct mild saturations, but there's very little we can do in this case. To saturate. I guess if you do like profile modeling in your careful way, there could be a way to back it out, but it needs a lot more work.
But with a huge error bar, probably.
Yes, agree.
Other questions? Oh, yep.
I have a question, data related.
Yeah.
Are you having any issues going from DR5 to DR7?
Yes.
Should we talk?
Yeah. So I finished on a DR5 actually a long time ago. I sat on there for a long time because I wasn't feeling confident about my data analysis. But then I convinced myself that's actually totally cool. And for DR7, I realized there are a few things. Like DR5, on the stator spectral signal to noise ratio are quite uniform. In DR7, it's not the case. I have some stars showing carbon-4, silicon-4, p-signal profile has very low signal-to-noise ratio. So in that case, my continuous fitting method actually falls apart. I have to find a different method to deal with it. So I do find issues with DR7. So that's why for this high-level science product, I decided to stick with DR5 because I feel very comfortable with it. And I would like to vet DR7 more. Yeah.
I think this is because we added a bunch of, all the archival data, really.
Yeah.
All the archival data. For lunch? All right, well, thank you, Young, and all the speakers. And we will reconvene at 1:30. 1:30, see you then.